I'll get started. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you again for this class. Just ask you to be glorified in what we do, and that we just answer any questions that remain about the homework, Lord. In the name of my prayer, Lord Jesus. Amen. So, ask away. Yep. 333. So that one, the way to do it, you get integral from 0 to 1 of x squared times 1 plus x cubed to the 10th power dx. So what I would do here, I would let u equal 1 plus x cubed. So du would be 3x squared dx. So like x squared dx would be du over 3, right? And then what's u of 0? So that'd be like 1 plus 0 cubed, which is 1. And u of 1 will be 1 plus 1 cubed, which is 2, right? And so if I, go ahead here, when I change I have to change the bounds. 0 goes to 1, 1 goes to 2, as it happens. And this x squared, the x squared dx becomes my du over 3, right? See that? Like this and this are that. So I just trade that for a du over 3. So I've got u to the power 10 times du over 3, right? Then you probably can finish from there, right? I mean, you're just wondering about the answer being weird, or?
No, I was trying to figure out how to set it up.
Okay. That's okay. There's no forgetting. There's just learning at the moment. So, but yeah, if we had a cubic, such that the derivative of the cubic is the square outside, then probably you want to make that like the u. And then because it's got bounds, I had to change the bounds, but So the answer involves like a fraction with a 33rd, I think, and so forth, right? But excuse me. Other questions? Yeah.
348.
348. That sounds scarier. Oh. This one's harmless. What's your question about it?
I guess
How to get started?
yeah,
All right, so let's look at this. We've got integral of dx over e to the x times the square root of 1 minus e to the 2x. Well, minus 2x, right? So as a point of order, like the only way we have to integrate things with radicals in the denominator, unless we remember some more complicated derivative of an inverse hyperbolic that we maybe talked about for a minute. But the thing that everyone's expected to know is that the derivative with respect to theta of inverse sine is 1 over the square root of 1 minus theta squared, right? This we all know, quote unquote, right? So that informs us that the integral of du over the square root of 1 minus u squared is inverse sine of u plus a constant, right? So with that in view, you should be looking to somehow use that for this problem, because that's at least a plausible plan of attack, all right? So with that in mind, let's rewrite this a bit. We could rewrite this as the integral of e to the minus x upstairs, right, times the square root of 1 minus e to the minus x quantity squared. See, because the laws of exponents say that like e to the s to the t power is equal to e to the st, right? Like that's how laws of exponents work. And yeah, if I write much more, I'll solve the problem. What would you let u equal to? I'll let you solve it. U equals e to the negative x. That should help out, yeah. Be careful, there should be a minus, right? Because like du will be minus e to the minus x dx, but, you know. So yeah. Try u equal e to the minus x. Other questions?
51.
Ooh. Yeah. Oof. Ah. Yeah. X to the 5th over 1 plus x to the 12th dx. Huh. All right. Well, what's that? It's a minus? I want it to be a plus, though. I'm putting a plus there. I'm going to put a plus there so I can solve it all the way to the end. We'll have to do something different. Yeah. Not too different, though. So, all right. If I see something like this, first thing I do is I try to make the denominator equal to u and see if a u substitution works. A moment's inspection quickly reveals that doesn't work, because we'd need like a u to the, we need like an x to the 11th upstairs for du to make that substitution. That's not going to work. So the thing that it is reminiscent of is like, well, let's see here. We know the integral of du over 1 plus u squared is inverse tangent of u plus a constant, right? So maybe, oh yeah, that's going to be it. So I just do integral of like x to the 5th dx. I think of this as 1 plus x to the 6th power squared, right? And so I've got like integral of du over 6 over 1 plus u squared. So I have to, you know, x to the 5th dx is du over 6. And yeah, so I get 1/6 inverse tangent of u plus a constant, also known as 1/6 inverse tangent of x to the power 6 plus a constant. Yay. You're like, but my homework problem has a minus. So what do I do? Anybody get any ideas? How do, yeah.
Doesn't like the integral of 1 over 1 minus u squared equal hyperbolic tangent?
Yes. Yeah, I think that's the deal. So du over 1 minus u squared is actually inverse hyperbolic tangent of u plus a constant. So that indeed is the secret sauce here. Now, admittedly, there are strings attached to this. This is only for -1 less than u less than 1, because that's the domain of inverse hyperbolic tangent, which happens to be the range of hyperbolic tangent. The more general answer without those strings attached has to wait for calculus 2, where we learn something called the technique of partial fractions. Partial fractions will give us another insight into how to do this integral, but that has to wait for calculus 2, okay? So for now, we just know this. Yep.
342b, what would you make
342b. I'd let u equal square root of x. Yeah. Like anything, you know, like integral of e to the square root of x over, say, square root of x dx. I've got like integral of e to the u. If u equals square root of x, du is dx over 2 root x, which means that 2 du is equal to dx over root x. So we got 2 du. So like this one would be 2 times e to the square root of x plus a constant. There's a pretty similar example to 342b. Yeah. Other questions?
I guess, how to start off with 337?
Oh, that's just FTC3. You just need to apply FTC3 for 337. Yeah. So look back at what we talked about that before. Fundamental Thermocalculus Part 3. So basically you just evaluate the integrand at the upper bound, multiply by the derivative of the upper bound, and then subtract the integrand evaluated at the lower bound times the derivative of the lower bound. So it's like f of b times db dx minus little f of a times dA dx. This is FTC3 for that one. Oh, no, no, no. No, no, no. You're not actually supposed to do the integral. No, 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 no. I will warn you guys, like, problem, none of you guys have asked me about it, but problem 352, it's a doozy. 352 took me a minute. And 353 is also, it's got some steps. So 355 on the other hand, the denominator is actually a square. So 355 is actually pretty easy because you can let you can factor the denominator for 355, and then that makes it easier, okay? 360 we talked about already, actually. So if you missed that, go back and look at it. But okay, so you guys want me to talk about 352?
Yes.
All right. All right, so so problem 352, you're up against the integral of x squared dx over 2x squared plus 4x plus 1. All right? So like the first thing I do is notice that this is a quote-unquote improper rational function. What do I mean by that? I mean, I've got a quadratic where I've got a quadratic upstairs, I've got a quadratic downstairs, right? So like the first order of business whenever you see something like this is to do long division or do some algebra to convert it to like a polynomial plus a rational function. That's like the first thing. Unless, of course, by some magic, you can just let the denominator be u and things happen, but that would be surprising. So, all right, so like, here's the long division. Oh no. So I've got x squared in my numerator, and I'm dividing 2x squared plus 4x plus 1 into it. So to get the 2, I need a half. And then that gives me x squared plus 2x plus 1. I subtract, and I get minus 2x. Oh, my bad. What happens 1/2 times 1 is what? 1/2 times 4 is 2. 1/2 times 1 is 1/2. So I get 2x minus 1/2. There you go. That's my remainder. So this here is actually the integral of 1/2 plus, well, let me put a minus here, minus 2x minus 1/2 divided by 2x squared plus 4x plus 1 dx. All right. Now the 1/2 we can integrate, right? That's easy. X over 2, yay, done. And then minus the integral of 2x. That was plus a half. If I factor the minus out, that's a plus, right? So 2x plus 1/2. I factored the minus out. Over 2x squared plus 4x plus 1 dx. So then what? So guys, like, as we deal in this course with integrating something in the denominator, like, there's really 3 different things that can happen, and you've got to have a different plan of attack for each one, all right? So think about it this way. If we complete the square, right? If you complete the square, and it's basically that pattern, or it could be this pattern, right? Or what's the other thing that could happen? You could just have the whole thing is a square. All right? Those are the 3 possible things that can happen in completing the square. Either you get the square plus a number, square minus a number, or just the whole thing is a square. That's like problem 355. The whole thing is a square. All right? So like, for example, if I have, example, what am I on? Whatever. 1. Haha. Integral of, say, like x dx over, x squared plus 6x plus 9, right? If you make the denominator equal to u, it's going to be very frustrating. It's not going to work, right? But if you factor, which is, by the way, just completing the square here, then you see, oh, I can just let u equal x plus 3. I get, x is u minus, so I get like u minus 3 du over u squared, which is like integral of 1 over u minus 3 over u squared du. And let me not finish it, but you see you can do it, right? If it's a square, we can do something like this. That's problem 355. It's like that, all right? So what's the kind of substitution you're going to use here? Here you're going to use like inverse tangent and the u equals denominator. Here you're going to use inverse hyperbolic tangent and the u equals to the denominator. Depending, like both, you need both. I don't want to do this problem for you because I want you to work it out for yourself. Excuse me. But let me give you a similar but different example that I work out in detail. So can I erase that, right? Yeah? Yeah. Can I erase this? Okay. So for instance, suppose you're up against like the integral of, say, dx over x squared plus, oh, I don't know, 4x plus maybe 9? No, 8. All right. So this is the integral of like dx over x plus 2 squared plus 4. All right. So this one might have been too nice. Well, okay, anyway. So this is the integral of du over u squared plus 4. What do I do then? Where we factored the 4 out? Right, and then we let w equal to u over 2. And so 2 dw is du. And so we get like 1/4 integral of 2 dw over 1 plus w squared, which is 1/2 inverse tangent of w plus a constant, which is 1/2 inverse tangent of u over 2, but u over 2 is actually x plus 2 over 2 plus a constant. So like, this is how we deal if the denominator has a positive square. But the thing that, what if I had like, instead of dx in the top, I had what? Like, if I had instead had up here, like integral of say, 3x plus 1 dx, how would I have dealt with that? Similar but different problem. So the way to deal with that is there's two things that go on. The one is to like let the denominator, let's say be, I used u, I used w, let's let it be, I need another letter, guys, help me out. I? Oh, y, okay. Y is x squared plus 4x plus 8. See, if I do that, then dy is 2x plus 4 dx, right? So for the sake of me, so I take this right here, right? And I convert it to the integral of 3 halves times 2x plus 4, I think. Sorry, guys. That will give me back the 3x I have up here, right? But then to be fair, what have I done? I've done what? I've added 12 over 2 there, right? Which is also known as 6. So I have to subtract 6 to be fair. So minus 6. The 1 is still there. Okay? And then the thing is, this will be equal to 3 halves the integral of 2x plus 4 dx over x squared plus 4x plus 8 minus 5 times the integral of dx over x squared plus 4x plus 8, okay? So the left piece, we can make a y substitution there, all right? Like dy, this is literally dy over y. So this gives me 3 halves natural log absolute value of x squared plus 4x plus 8. And then the other piece is 5 halves inverse tangent of x plus 2 over 2. How do I know that? Well, I just worked it out right over there. So this is what I'm talking about. It's a mixture of a log like a u substitution for the denominator, and then whatever junk doesn't fit into that becomes an inverse tangent if the denominator is the sum of squares. Same thing kind of thing happens if it's a difference, except you have an inverse hyperbolic tangent to pick up whatever. I think of it this way. I try to put everything I can into a denominator equals like a denominator substitution. Whatever doesn't fit into that, I pick up with either the inverse tangent integral or the inverse hyperbolic tangent integral. All right? And when you complete the square on this, I think you get a difference. So that ends up, this one ends up being the inverse hyperbolic tangent kind of thing. Oh, I better let you guys get started on the quiz. You need time for it, right? So let's get going. There are 4 problems. I think, well, anyway, hopefully you can get 3 of them well, and